Welcome to Math 2320. This is section 2.1. Here in question 1, we have a simple differential equation. The derivative of y with respect to x is x squared minus y squared. So what is this thing in blue here? What this thing in blue is a direction field. Think of it as a set of steering currents if you're talking about a hurricane. Or if you're looking at the weather at night, they'll show you arrows which indicate the wind patterns. So what this is if you pick a particular point here in R2, then the slope at that particular point is determined by the thing on the right hand side. So for example, when x and y are both 0 and you're here at the origin, then the slope of the steering current is 0. If we're at the point -2, 1, see, that's what they're giving me here, -2, 1. So x is -2, y is 1. The slope there then is -2 squared minus 1, which is 3. So at that particular point in the plane, if I drew a small little line, I would see that the direction is going in the slope of being 3. So think of it this way. If I started off at any one of these points, the arrow is going to direct me on my particular path. So in our problem, they're asking us which of these graphs is actually correct. Well, let's see. -2, 1. Well, the red line isn't there. -2, 1, not there. And if we get here to this particular line at -2, 1, notice the solution curve, which is going through the steering currents, is there at that particular point. So what about if we have an initial starting point at 3, 0? Well, 3, 0 would mean I'd have 3 squared minus 0 squared, which is 9. So at the point 3, 0, I'm going up fairly steeply. So if I'm looking at my graphs again, I'm looking for 3, 0. And is this going up very steeply? The answer is yes. If I picked another point for 3, 0, notice there's no even solution curve at those places. All right, what about at the initial point 0, 2? Well, look here, there's no solution there. What's going on at 0, 2 is I've got 0 squared minus 2 squared. So the slope should be pointing downward at that initial position of 0, 2. So here is 0, 2, and yes, the direction of the flow is going downward with a slope of -4. What about 0, 0? Well, at 0, 0, I've got 0 squared minus 0 squared, which is 0, so it should be perfectly flat. And so if you look right here at that particular point, notice the steering current or the direction flow is with a slope of 0. The others don't even pass through 0, 0. All right, we have a new flow pattern here. All right, what about at 0, 0? Let's see, 1 minus 0 times 0. So I have a slope of 1. So notice you can kind of see how the flow would go depending upon where you would start. If I started here, the flow is up. If I start here, it's going to come up and it might take me over and down. If I start down here, the flow is directing me downward. So we're starting off at the origin. No, 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 yes. So notice if we start off there, we're stuck in this particular flow stream or flow pattern. What about minus 1, 0? Let's see, 1 minus, well, minus 1 times 0 is still 0, so I get a slope of 1 at minus 1, 0. So here's minus 1, 0. Notice the flow is up, and the direction that we would travel is going in this direction. All right, what about at 2, 2? No, maybe. I can't see it. Let's see. At 2, 2, I've got 1 minus 2 times 2, 1 minus 4, so a slope of minus 3. Let's see. So yes, here at the point 2, 2, you can line up 2 and 2, and my flow is downward. So the flow pattern would look like that. What about at 0 minus 3? Let's see, not even there. Here is 0 minus 3. And let's see what's going on there. Well, 0 times minus 3 is still 0, and the slope here is coming upward at 1. So the flow pattern looks like the following. All right. So what about what's going on here? Well, now what they have is dy dx is, and the direction field is generated by a function. And that function is this graph. So what is this graph telling me? Well, when y is 0, the slope there is 2. When y is minus 1, the slope is 0. And when I've got something under 1, I don't know, 0.7, 0.8, the slope there is again 0. So I'm going to try to match that up with these direction fields that they're giving me. So let's see. I don't really care about x. What I care about is y. So when y is 0, so right along here, here's y equals 0. Notice all of these little lines have an upward arrow. Yeah, we can say it's about 2. And if I come here to, so here was y equals 0. Here's y is a little bit under 1, so I'll call it 0.8. And here's y is minus 1. Perfectly flat. And if I'm under that, then the slope becomes more negative. And that's true. Looking here for this segment, when y goes from minus 1 to minus 2, here's minus 3. Once I pass in this section, the slope is again positive. So notice all these y's here, the slope is negative. When I reach a y close to minus 3, it flattens off and then becomes positive. All right, on this particular problem, we're looking at isoclines. When is my direction field a particular constant? Now, continuing on this problem, we're looking at the isoclines. we're looking at when the velocity field or the flow field or the direction field is constant. So in our case, this is x plus y is equal to a constant c, and that c can be any number between -5 and 5. Well, what does that mean? Well, if c is 0, x is minus y, or y is minus x, and so you get this downward line through the origin. And as you change the value of c from 0 up to 5, what you see is it's minus y plus 2 minus y plus 5. And so what we get are lines that all have the same slope of -1, just shifted up and down. Okay, so in this case, we're looking at the initial condition y at 0 is 1. All right, so we're looking here at this particular situation. So scrolling down here, we see on this problem, the second one, this one is correct. Now, why is this correct and the first one was not? Still have the same downward slope lines. We have y at 0 is 1, so it's at this height. That is the starting position. What about the slope there? Well, the slope there is x plus y. So 0 plus 1 is 1. And so the slope here is an upward line with a slope of 1. Whereas in this picture, if that's the initial condition, this is a downward slope of -1. And at 0, 1, we need +1. In this one, we say, well, why couldn't it be this one? Because y at 0 is 1. This has a slope of 1. But what you notice here is wherever you move, the slope is always 1 on these lines. And in this case, well, that just isn't true because this slope changes as we move from place to place. All right, what about this one, x squared plus y squared? Well, depending on various c's, 1/4, 1, 9/4, and 4, what we have are concentric circles. All right, so we have concentric circles here, and we have a various circle. So the question is, well, which one of these is right? Well, first off, when you have x squared plus y squared, it doesn't matter where you are in the plane, x squared plus y squared is always 0 or positive. So I can't have these negative slopes. All right, well, let's see. All of these seem to have positive slopes. That's a possibility. And these have negatives, so no. So this one has a positive slope. That's good. So does this one. So they both have positive. So which one is it? So let's see. If we are at 0, 1, let's see. At 0, 1, we have x squared plus y squared, slope of 1. Over here at -1 something, slope is still positive, and so this is our particular trajectory through y at 0 is 1. Alright, now in this case we're looking at critical points and the phase portrait. So we take our direction field, set it equal to 0 to find the critical points. So factor out the y, and so the critical points are 0 and 2. Alright, so I've got 0 and 2 as critical points, so pretty clearly this first one is not correct because I've got 0 and minus 2. Let's see, this one is 0 and 2, possible. 0 minus 2, no. So let's see, why is this particular graph the correct one? Well, let's see. When y is bigger than 2, this is positive, and so the slope is upward. So you see anywhere along here, we're moving upward. If we are between 0 and 2, all right, the lead part is positive. 0 or 1 minus 2, this part is negative, so the slope is negative. And so for anything between 0 and 2, we're moving downward. We're moving downward to the next critical point, which is at 0. Well, what happens if I have a starting point under 0? Well, let's see, if this part is under 0, that's negative. This is negative. The product of two negatives is positive, and so it's moving upward. So, any points around 2, if they're above 2, they're going to run off to infinity. If they are under 2 but bigger than 0, over time they're going to decrease to 0. Anything under 0 is going to just decay to 0. Alright, so there's that. And the question is, are these stable or unstable? 2 is not a stable critical point because anywhere around it moves away from it. And asymptotically stable mean it's drawn in. The limit over time is going to 0. So what about the solution curves? Well, let's see. If I started off with a y anywhere around 2, well, if it's bigger than 2, it is moving up. If it's under 2, it's drawing down toward y equals 0. Anything under 0 moves up towards 0. And so here's the picture of our phase portrait. Okay, so let's see. In our last problem, we are looking at something from mechanics. We have the mass times the velocity, change in velocity with time, depends upon mg minus kV, which is a term representative of air resistance. So this is a body falling from a great height. So what happens? Does it keep getting faster and faster as it falls to the ground, or is there a limiting factor? So let's see. Let's look at the critical point. So if you divide through by m, you get g minus kV over m, set that equal to 0, and you get that v is mg over k. And so this is a limiting velocity because any value of velocity bigger than it moves down to that particular velocity. So for example, it's thrown out of the airplane with a particular speed. The speed will decrease to the terminal velocity. And if it's just let go out of the airplane or something, then the speed is going to increase until it reaches the terminal velocity.